So, picture this. Your agent works perfectly. Then you add a second agent, and it just breaks. You try to speed things up with parallelism, and suddenly your state is a corrupted mess. You add a simple retry loop, and the agent gets stuck forever. Or you add human approval, and the entire graph just deadlocks. Sound familiar? Yeah. Every tutorial out there shows you how to wire nodes together, but nobody really explains what's actually happening to your state object underneath. Well, today, we're going to fix that. This is the LangGraph State Design Guide that honestly should have existed from day one.
Okay, let's just dive right in. The very first thing you have to get your head around is that state in LangGraph, well, it's not really a Python dictionary, not in the way you think. It's much more like a shared communication bus. See, every node can read from it, and every node can write to it. But here's the catch. The framework, not you, gets to decide precisely when those rights are actually applied.
And the reason it works this way is because of the core execution model LangGraph uses. It's called Pregel. It's the same model Google uses for absolutely massive scale graph processing. Now, the crucial point here, the thing you have to remember, is that nodes running in parallel never see each other's writes while they're running. They each work on their own little isolated copy of the state. This isolation is fantastic. It's a great safety feature, but it's also a massive trap if you don't design your state schema correctly. And that brings us right to the most common mistake I see everywhere. On the left, you've got what most tutorials show you, a simple list. This is a ticking time bomb because it will silently corrupt your state. Why? Because LangGraph's default rule is last write wins. So if two nodes write to your messages list at the same time, one of those writes just disappears. Poof, gone. The right way, over on the right, is to use Python's annotated type hint. This lets you attach a little extra note, in this case, a special function that tells LangGraph how to merge those concurrent writes together instead of just letting one overwrite the other. So, this leads us to what is, without a doubt, the single most important rule of LangGraph state design. Seriously, read this, memorize it, write it down. This isn't just a suggestion, it is the fundamental principle for building any kind of parallel safe agent. If you ignore this rule, your state will, eventually, become corrupted. It's not a matter of if, but when.
One of the coolest things about LangGraph is that it automatically parallelizes nodes whenever it can, which is awesome for speed. But as you're starting to see, it's also a trap if you haven't really thought through your reducers and your overall state design.
Okay, so let's make this real with a concrete example. Here, we've got a web search and a database lookup running in parallel. Now remember, they each operate on their own isolated copy of the state. After they're both done, their individual writes are collected by the framework. And then, and this is the key, only then does that add reducer you defined kick in to merge both sets of results into the main state. And this just perfectly illustrates why, without that reducer, you just silently lose the data from one of these nodes every single time.
You know, the next anti-pattern I see all the time is just bloated state. It's just like with databases, right? You need to normalize your agent's state. On the left, you see this mess where every single agent sees every single field. It bloats your context and makes debugging a total nightmare. On the right, we've cleaned it up. We've normalized it. Subagents have their own private state, and the parent graph only holds the absolute minimal shared state it needs for orchestration. The rule of thumb here is really simple. If a field is only needed by one agent, it does not belong in the shared state schema, period.
All right, so our state is designed correctly. Now let's talk about making agents that can actually survive out in the real world. And that means handling failures, handling pauses, and collaborating properly between multiple agents.
Checkpointing is, well, it's basically a save file for your agent. At every single step, LangGraph can save a complete snapshot of the entire state. So if your agent fails at step 9, you don't have to restart from the very beginning, you just resume right from the last successful checkpoint. Now, for development, the in-memory saver is totally fine, but for production, you absolutely must use a durable saver, something like Postgres saver.
And believe me, this isn't just some minor feature. Checkpointing is what enables the three most critical capabilities for any serious agent. Fault tolerance is the obvious one, but it's also what lets you build those human-in-the-loop workflows where the graph can just pause for hours or days waiting for an approval. And for debugging, it's a lifesaver. It lets you time travel and inspect the exact state at any point in the agent's history.
So when you have multiple agents, how should they actually talk to each other? Well, there are three main patterns. A network is super flexible, but it can be chaotic and unpredictable. A supervisor is probably the most common pattern you'll see in production. You have a central router LLM that delegates tasks to specialized agents. It's predictable and way easier to debug. And then you have hierarchical, which is really for when your system gets so complex that one supervisor just can't manage everything anymore. And hey, don't just take my word for it. This is the explicit recommendation from the LangGraph team themselves. Don't over-engineer this stuff. Start with a supervisor model. It's powerful, it's debuggable, and it's what companies like LinkedIn and Uber are actually using in production. You should only scale up to a hierarchy when you absolutely have to.
All right, time for a rapid-fire review. Let's go through the 5 state design sins that will absolutely destroy your agent in production.
First step, never, ever mutate state directly inside a tool or some other callback. Doing this completely bypasses the reducer system and the entire safety model of the graph. All state changes must come from the return values of your nodes.
Yeah, I know we've already covered this, but it is the #1 cause of data loss, so it's worth repeating. Any list that multiple nodes might write to, like your messages or tool outputs, it absolutely needs a reducer. Otherwise, you're just gambling with last write wins.
Letting your chat history grow forever is just a fantastic way to burn money. I mean, every single LLM call has to pay for that entire history and tokens. You need to have a node that trims or summarizes the history before passing it to your main LLM.
You have to treat your state as if it's immutable. If a node gets a list from the state, it should not, under any circumstances, modify that list in place. It has to return a brand new, updated list. Mutating shared objects directly is a recipe for completely unpredictable behavior that even your reducers can't fix. And finally, using the in-memory saver in production is a guarantee of total data loss. It's that simple. The second your process restarts, for any reason, every single agent's history is just gone. Forever. Please use Postgres Saver for anything you actually care about. Now, why does all of this technical discipline actually matter? Well, it's not just about making sure your agent works correctly, it's also about cost. Every unnecessary field you have in your state costs you in storage, it costs you in latency, and it costs you in tokens. A well-designed, normalized state can be up to 70% cheaper to run per invocation than a naive, bloated one. So here it is, the final checklist. Every field that gets appended to needs a reducer. Give your subagents their own private state. Use a durable saver like Postgres in production. Trim your history. Treat state as immutable. And use the command object for clean multi-agent handoffs. You know, state design is definitely the hardest part of building production-ready agents because it requires you to understand the runtime, not just the API, but now you understand both.